So for our initial setup here, I've already got a light bulb and socket hooked up to a clamp on a pole, metal pole. So you're gonna wanna set that up right away. I used the 150 watt light bulb. The wattage shouldn't make a huge difference here, but I would trend towards the higher wattage light bulb. So in our case, our highest watt light bulb in the classroom right now is 150. I've got a photovoltaic solar panel cell. You can find that up in the front. Got a couple extra alligator clips, so black and red alligator clips. We're gonna need those. I've got a light sensor out, so you're gonna wanna grab a light sensor box. Another sensor we need, energy sensor and a variable load. So we'll need both of these, LabQuest, and an iPad. So that's what we need for initial material. So the first thing that we're gonna do here is hook up our energy sensor to our variable load. I told you we're gonna need these alligator clips. That's what this is gonna be for. So you should have a set of black and red alligator clips. You're gonna hook it on black to black and red to red. And you wanna make sure that once you've got them hooked up, you wanna screw these tight so that it holds your alligator clips in place. Once I've got my energy sensor hooked up to the variable load, for the source, I'm going to plug in my photovoltaic cell. So again, red to red, black to black. Once I've got this guy hooked up, I'm going to hook up my energy sensor. There's two plug-ins. I'm going to hook that up to my LabQuest. To look something like that. And then we might as well right now take out our light sensor, take that out of the box. We're not going to use this right away, but set it to 0 to 6,000. So we don't have to worry about that when we run the trial in just a second here. And I'll hook that one up too. So it should look like this. You know, you got 5 variables that you're looking at once you have it set up properly. For trial 1, we're going to be measuring from the bottom of the light bulb to the photovoltaic solar cell. It needs to be 20 centimeters. So I already pre-measured this, but what you got to do is come out here, take a meter stick, and you're going to measure that the bottom of the light bulb is at 20 centimeters from the photovoltaic cell. You want that light bulb and solar cell to be lined up. And you can adjust it as you go, but you want to make sure that the bottom of the light bulb is lined up to the photovoltaic cell. At this point, I can turn the light on. You can have the light on for a while here. So I'll turn the light on. Make sure that my cell is right under the light bulb. And you should be getting a reading at this point. Take your variable load, and what we're looking at here is the power. So I'm going to adjust my variable load. I'm going to try to find, so you're adjusting the resistance to find the greatest power. So I'm changing this, moving this up. So it looks like I'm in the 20 milliwatt range here. So it keeps going up and up. Again, we're keeping an eye on the power. And you want to find the highest power. And so you're going to keep adjusting this until you hit your maximum power, and then it'll start to go down. So it looks like mine is already going down. I might have already found my maximum power. Go a little bit further just to make sure here. Yep. So I'll take it back. Looks like right around here is my maximum power. So once you've found that, we'll turn the light bulb off. So once I found my max power, turn the light bulb off. What you want to do is 0 current and potential. So we're going to click on current and potential. We're going to zero both of those numbers out. And then we'll turn the light bulb back on. You can play around with the variable load a little bit again to see if you can kind of push that power a little further. Looks like mine, it went up another milliwatt or two if I adjust it a little bit here. So that should be good for that. The very last thing you need to do here, so I'll pan back out, is to get an accurate light sensor reading. You need to hold the light sensor kind of at the bottom of the table here. So you want it to be, the tip of the sensor to be pointed at the light bulb, but also kind of at the bottom of the table here. You want it to be even with the photovoltaic cell. And so that looks like a good reading. So this is the data that you're gonna, once you're satisfied with this, you're gonna hook this up to your LabQuest. I'll show you that in just a second, but you're gonna hook this up to graphical analysis, and we'll analyze the data. For trial 2 here, same idea as trial 1, except you're going to be moving the light bulb so that it's 40 centimeters now from the bottom of the light bulb to the photovoltaic cell. Obviously, you want to hold the meter stick straight, unlike I did in this selfie here. So 40 centimeters from the bottom of the light bulb, you're going to turn the light back on, find your max power by adjusting the variable load. So you're going to want to move that variable load a little bit, even though it might be, at that point near the max power for all of these once you've adjusted it in the initial one. You're going to hold the light sensor up, so you got to make sure you hold this light sensor up so at the base of the table, and you want it pointing towards the light source once it's on. And when you have all of that, when you're satisfied, you're going to take a screenshot from graphical analysis. So you want to make sure it's still hooked up to graphical analysis, and these are all live meter readings, so you're not recording any graphical data. You're just getting these live meter readings on graphical analysis, taking your screenshots from there, rather than taking them directly from your LabQuest. So I want to see that you have those screenshots on everyone's iPad, so everyone should be hooked up to graphical analysis for this. Trial 3 here is going to be the exact same thing, except now we're at 80 centimeters. For some of you, you might not be able to get it up to 80 centimeters. Looks like I wasn't able to on here. So if you can't get it to 80 centimeters, go as high as it'll possibly let you. Obviously, you don't want to get silly with this because the light bulb will topple over, fall off, and break. But you want to get as close as possible to 80 centimeters for trial 3. And then same idea, turn your light back on, find the max power, make sure the light sensor is held up and pointed at the light bulb, and you're going to take a live reading from graphical analysis again. So you should have 3 meter readings that are going to go into your final lab report here. On the lab write-up, you have to find area of your solar cell. So you should be doing this with your own meter stick or half meter stick. But I'm going to show you what I did here. So you're just measuring the length and the width of your photovoltaic cell. And so you're going to ignore that outside bezel. You're just getting that main part of your photovoltaic cell when you're doing your measurement. So my width was 5 centimeters. My length was 10 centimeters. So 5 centimeters times 10 centimeters is going to be 50 centimeters squared. So that's my area, and that'll come in handy in just a little bit here. For the rest of the video here, I'm going to be walking you through some of the math that you're going to encounter in the data table on the second page of the solar power worksheet here. Before you do anything, make sure you put in your meter readings that you got for your 20 centimeter, 40 centimeter, and 80 centimeter trials. Mine got a little bit messed up for the luminosity on my 20 centimeter trial, so I had the sensor plugged in differently, and so my luminosity value is actually on the top of the meter reading here. And that's okay as long as you have all 5 variables. It shouldn't matter where they are on that meter reading when you put it into Notability. So we actually already measured out the surface area of the solar panel, if you remember from a little bit earlier in the video. And for the photovoltaic cell that I use, the surface area was 50 centimeters squared. The next thing we're going to want to do is convert that 50 centimeters squared into meters squared. So many of you probably know how to convert centimeters into meters, but the conversion for centimeters squared to meters squared is actually a little bit different. And so 50 centimeters squared is actually going to equal 0.005 meters squared. If you don't know how to do that conversion off the top of your head, I would suggest using the conversion calculator in Google here. So 1 square centimeter is 0.0001 square meters. So it's a factor of 10,000 instead of a factor of 100 when you're doing your conversion. And so you can type in here 50 square centimeters is 0.005 square meters. To find the power per square meter of solar panel, we're going to take our power output in watts. So let's go back up to our meter reading here. We got to find the power output in watts. And we do have a power output. So for my 20 centimeter trial, it was 30.7. Now this is really important. This was milliwatts. So 30.7 milliwatts, but it's asking us to convert that into watts. So let's put that down here. 30.7 milliwatts. .7 milliwatts is going to equal 0.0307 watts. Again, same idea. If you don't know how to do these conversions, this is a normal factor of 100 conversion. We can use the conversion calculator here in Google again. So 0.0307 watts. And so we have to take that power output in watts, so we're not done here yet. .0307 watts divided by the total area of our solar cell, so that was what we just did above. 0.005 meters squared. And so when you do the math for that, I'm getting 6.14 watts per meter squared. Obviously your numbers are going to be a little bit different, but this is the same idea. It's the same idea. You're converting your centimeter squared into meter squared and your milliwatts into watts. So those are important conversions to do. Otherwise your numbers are going to get thrown off a little bit here. To find the available power per square meter, we're going to use our light sensor reading actually. So we'll go back up. This is our luminosity. So this is why I made note earlier that my luminosity was a little bit wonky here for this first one. Mine is actually up here. So 2100 lux. And we're going to take that luminosity value and divide it by 75. And that's a conversion factor. We're going to convert this into watts per meter squared. And so when I do the math for that, I get 28 watts over meters squared. So the last little bit of math we have to do here is to find our solar power efficiency. And so to do that, we're going to take our power per square meter of solar panel. And that was the number I had in this teal column right here. So 6.14 watts per meter squared. and we're going to divide that by the available power per square meter. And that was the number we got right here. And then we're going to take all of that and multiply it by 100. So when I do that, my solar panel efficiency turned out to be 21.9%. And so what that means is that 21.9% of the total amount of light that was coming into my photovoltaic cell was actually being converted into energy. So that's our solar power efficiency. And so I'm going to let you figure this out. So this is going to be the same process. I would follow through with this video for the 20 centimeter distance if you don't know how to do that. And then it's going to be the same idea. Obviously your numbers are going to be different for your 40 centimeter and 80 centimeter distances, but you're just plugging in the numbers that you found in the data sheet and putting it into this data table. Let me know if you have any questions with the rest of the question prompts on this lab sheet, or if you have any questions with the lab procedure in general. This was our solar power lab. Thanks for watching.